Hello students, welcome to the video on the integration of other circuit elements, a part in the module 5 of our subject electronic devices. So here in this video we will be discussing how to fabricate or how to integrate the other elements like diodes, resistors, capacitors in an monolithic IC. So we know that monolithic IC is nothing but any circuit can be implemented in it using a single wafer. So here we know that a transistor can be fabricated using a process called as the first one will be the substrate followed by the buried collector region, then the base along with the emitter. So this will be formed as three different layers. So diode is a two-layer device. So I need only two layers, either PN or NP. So how to obtain a diode? So in a transistor, a diode can be formed by taking the PN junction or the emitter to base junction by sorting the collector to base junction. A simple method to build a PN junction diode is like you take a P-type substrate, use the N region, you dope it with the N region followed by a P region. Now I take two contacts, one from the P region and the other one from N region, which act as anode and cathode respectively. So this can be obtained in a transistor by taking the ohmic contact from the emitter and the base region by short circuiting the base to collector regions. So by making proper connections during the metallization process, we can obtain a diode of required parameters from a transistor. So the next device we will be discussing is resistors. So the resistors are otherwise diffused or implanted resistor is nothing but where I will be using the PN layers, the shallow junctions, which is used for a transistor formation. We know that any semiconductor material, whether it is a P material or N material, will have its own resistivity property based upon the doping concentration. The more the doping, the less the resistivity property of it. So if I am trying to take out two leads from the two regions, which is isolated from other thing, like for example, if I have an N plus, this N plus region should be isolated on its all throughout the surface. Now, if I take two leads from here, so the internal resistance of this material will give me a resistance property. The resistance can be like, it can be of two, one is like a linear resistor and the other one is a serpentine resistor. So the serpentine resistor will give me a high resistance value in a smaller region. So here when I come for the fabrication of a resistor or integrating a resistor, we will be having different layers. So just you take an aluminum contact or ohmic contact from 2 points in a single layer, which will give me an resistance. So the equivalent resistance of this is given here in this diagram here. So the next one is what is meant by capacitance. We know that capacitance is nothing but two electrodes which is separated by an insulating layer. So we have in a diode we have studied that there will be two types of capacitance. One is called as the junction capacitance and the other one is called as the dielectric capacitance. We can say that whenever there is a junction, we will be having a capacitance because any junction will be having an insulating layer. For example, if I take here P and this is an N, when I have a junction, I will be having an in between barrier region, or it is called as an insulating layer, with this P region acting as one conducting part and N region acting as another conducting part. So this is called as the junction capacitance, where this depletion region is separating the two electrodes. So a lead from here, from this P and another lead from this N region will result in a capacitance which is called as the junction capacitance. So the junction capacitance value will be varying with respect to the applied voltage. So the next one is we can have a dielectric capacitance which is same as our mass capacitor. So mass stands for metal oxide semiconductor. So you take a aluminum metal here, which is layer one, which is nothing but the one, and followed by a silicon dioxide layer, and this N is nothing but a semiconductor material. So here again we have the capacitance property. The silicon dioxide acting as an dielectric with one electrode is my metallic layer and the other electrode is nothing but my semiconductor layer. So this is nothing but a MOS capacitor, metal oxide semiconductor capacitor. So here in this example, we can see how a capacitor will be used in the memory circuit. So here we can see that we know that each bit can be stored in a capacitor, or a capacitor can store the bit either in the form of ones and zeros. So the charge stored will indicate the value stored. So here if I have an inversion layer present here, and the inversion layer, the amount of charge carriers which is present here will indicate the value which is stored here. So this data can be read using the bit line and the word line. So the top plate of the capacitor is a polysilicon, and the bottom plate will be an inversion layer which is nothing but the N plus of the transistor. So using this setup I can store the charge, or it can will be acting as a memory. So the next one is what is meant by interconnects. Interconnects are nothing but the interconnect wires, we can say the discrete wires what we see outside like when we use it in our lab is called as an interconnect. So I have various components, and these various components are tied together, or various layers are tied together to form the interconnect. So this will be the setup of an IC with the top layer removed. So the internal of an IC is given here. So the equivalent circuit indicating the various capacitive elements associated with this circuit for various interconnects are given here. So the interconnects are nothing but the pattern that ties all the integrated devices that like transistors, diodes, everything together. These interconnects are made by means of the aluminum metal. So aluminum is frequently used for the interconnects. So it can be a local or global interconnect. Local interconnect is nothing but where it will connect the two elements which is near to one another, and also we will be having aluminum as the main element because it is very much adhered to the silicon and the silicon dioxide material. The adhesive property is good and hence aluminum is used. But at high temperature, aluminum may try to react with the silicon, and in that case, we will be using a material like platinum or titanium. So in gallium arsenide material, when that is normally in photoelectronic applications, gold will be used as an interconnect. So here in this video, I mean in this slide, we will be discussing or we will be seeing how an basic monolithic IC circuit which is given here is implemented or it is integrated. So here we have a transistor. So we know that a transistor consists of three regions. So I will be having a collector region and then the base followed by the emitter. So this emitter is terminal 5 which is taken out here, and my collector is 4 which is taken here. The green color is nothing but the collector here. Now this base is connected to the cathode of the diode, and here we can say the base is connected to the cathode. It should be connected to the cathode, and both the anodes, two diodes anodes are connected. So the P region and P regions are connected together, which indicates that the anode is connected. And here I take a lead resistance. So the resistance is nothing but their point which is taken out from here. So that gives me the terminal 2, and terminal 3 is nothing but which is taken here. So like this, any type of integrated circuit or any type of an circuit can be implemented on a single substrate, and that is called as the basic monolithic IC. So a monolithic IC is nothing but any type of components, whatever we need can be implemented on a single substrate. So here we can see how we have seen how to integrate various components in a single wafer. Thank you.